Alright, so in this lecture we're going to put together a whole bunch of odds and ends as you work your way through the notes package. And one thing I want to warn you about is that we're going to be skipping lightly across a lot of stuff that I've given you lots of notes about. And all of the information related to the generation of action potentials I am going to skip over because in lab today we spent a lot of time on the interactive physiology website, and so I would encourage you to check that out. And I also have a recording. This is a recording I made last year, but it is of me paging through that interactive physiology website, and we're listening to what the nice lady has to say, and we're also listening to dadgummit, I got the cat sitting here, and he just started licking my screen, which was then paging through the PowerPoint presentation. Sorry about that. So, with all that said, then definitely want to spend some time with either interactive physiology on the online website, or watch the video that I made of me paging through it and providing a little color commentary as we go along. Alright, so let's get started on this process then. So the first thing we're going to look at is nerve fiber regeneration. When neurons are damaged, the bad news is that a mature neuron can't reproduce. And so if the neuron dies, then it can't be replaced. And the way to kill a neuron is to damage the cell body. And when that happens, frequently, other nearby neurons are also stimulated to die, which is a bit of a bummer. On the other hand, if it's axons or dendrites that get damaged, then the possibility of some regeneration is there. And so, for instance, in the peripheral nervous system, if we sever an axon, and this happens, injuries, cuts especially, a deep cut, may sever a neuron or an axon, but if the cell body survives, then it's possible that the Schwann cells that surrounded the axon will degenerate, and I've got this drawing here, I've turned it on its side. It works just as well on its side, but here we see the site of injury, and everything that is distal to that site of injury will degenerate, but the Schwann cells may survive, and if they do, they can secrete growth factors that will call the axon to regenerate and begin to grow through the tube that the Schwann cells make. And so these Schwann cells can help to redirect the axon growth along the original path. And if that occurs, then it's possible to restore nerve function in the area where the axons were damaged. Oligodendrocytes, on the other hand, in the CNS. Remember, oligodendrocytes provide the myelin sheath in the central nervous system. They do not have the neurolemma, and so when the nerve fiber degenerates, then frequently that, or all the time, that wrapping of the myelin sheath is also lost, and so there's no proliferation, and so axon regrowth does not occur in the central nervous system. So damage to a tract in the spinal cord or to a section of the brain is not repaired, and so that is why spinal cord injuries and traumatic brain injuries are so especially devastating to the person. Okay, as I said, I've given you a lot of information in your notes about nerve fiber regeneration, so this is all that we're going to cover here in the lecture. Okay, so now we're going to talk about the synapse and synapse structure. Now, the synapse is the functional connection. Now, of course, it's not a physical connection, because in a synapse we see an axon terminal come close to but not make contact with a neuron, a muscle, or a glial cell. And so there's always this space between the two, the synaptic cleft. It's a fluid-filled space, and this is where the axon terminal, so here's the axon terminal, approaches but doesn't touch what we talk about as the postsynaptic cell. So here we have the axon terminal of the presynaptic cell, because the information is coming this way toward the synapse. And here is a dendrite, let's say, of the postsynaptic cell, the second cell in this circuit. So the presynaptic neuron conducts a nervous impulse toward the synapse, and in response to that action potential arriving at the axon terminal, then we see, as we saw in the neuromuscular junction, calcium ions flood into the axon terminal. And in response, all of the vesicles that are filled with neurotransmitter, so here we see all the vesicles that are arrayed here. When the calcium goes in, they will come and perform exocytosis. They're releasing the neurotransmitters into the synaptic cleft. And here in this picture, I love this picture. Now this is falsely colored, so this is an electron micrograph. It's a scanning electron microscope that was used to make it. And then the scientists who produced this image have then added coloration later on. But what we're seeing here are all of the synaptic vesicles waiting there to dump their neurotransmitter across or into the synaptic cleft. And then once released, the neurotransmitters diffuse across and will bind to the receptors on the postsynaptic neuron. So that postsynaptic neuron binds the neurotransmitter, and in response we see a nervous impulse being transmitted away from the synapse. So it's the job of the postsynaptic cell then to receive the neurotransmitter and to start a small local potential change called a graded potential change to occur on the postsynaptic neuron's cell membrane. So there are multiple kinds of synapses. We've already talked about the neuromuscular junction, which is the synapse between a neuron and a muscle cell. And I've got two images here of neuromuscular junctions. You can see that in both cases we have striated muscle, so it's either cardiac muscle or skeletal muscle. And you can see here is an axon coming down, and then we can see all of the axon terminals here that are associated with this neuromuscular junction. And then, deep to all of that on the muscle cell itself is the motor end plate, where all of those receptors are waiting to receive the neurotransmitter. A neuroglandular junction is a synapse between a neuron and a glial cell, and again there's the same kind of construction here. We have an axon coming down to an axon terminal, and it comes close to but doesn't touch the glial cells to stimulate secretion or to stop the secretion once neurotransmitter is released. Let's see if there's anything else I wanted to say. Yep, I think that's got it. Yep. So, all right, now I'm going to talk a little bit about what happens at the postsynaptic cell when neurotransmitter is released. And in order to have that conversation, we need to talk a little bit about what's called the resting membrane potential. And the resting membrane potential, now, I really want to encourage you to spend some time reading what I've given you there about the basic principles of electricity in your notes. So that some of this will also make sense. I'll try to bring in that information as we're talking about it here, looking at the resting membrane potential. Now, the resting membrane potential is, if this is the let's say, you know, what we're looking at is a neuron here, and here's the cell body. Here are all the dendrites coming off of the cell body. Here's a nucleus, and then there's an axon. Oop, there we are. There's an axon that's leaving the cell body. If we were to look, say, at the cell membrane of one of these dendrites. So here we have a dendrite, and this is inside, so intracellular. Out here is extracellular, so outside the cell. What we would see if we could use a probe to determine what the electrical charge of the fluids and outside of the outside surface of the membrane, comparing it to the inside surface of the membrane, we would see that they are polarized, with the interior having a slightly negative charge compared to the exterior, which has a slightly positive charge. So the interior is always going to be the point of reference, and so what is giving it this charge differential is the fact that there are lots and lots of sodium ions on the outside, sodium, lots of it, and inside we see fewer potassium ions. So if sodium has a positive charge and potassium has a positive charge, how could it be that the inside is negative? Well, this is a relative negativity. It is less positive inside than it is outside. And so because of this less positive characteristic, we think about the inside in relation to the outside as being negative in relation to the inside being positive. So now, if they were the same, if they had the same electrical charge, then there would be no membrane, there'd be no potential difference. But since the inside has slightly less negative charge, then we express the resting membrane potential as negative 70 millivolts. And as I've said before, these are the same volts that that's the same unit of measurement that we use with electricity in our own houses. So if a 12-volt battery, let's say, the kind that you put into a smoke detector, that's a 12-volt battery. So that means that one side of the battery, the positive terminal, compared to the negative terminal, the difference in electrical charge is 12 volts. So we measure in a much smaller unit of voltage, though, in millivolts, thousandths of a volt. So the interior of a neuron is negative by 70 thousandths of a volt when compared to the exterior. And this resting membrane potential is maintained by the sodium-potassium pump. And so if this is the membrane again, and here we have this membrane protein that acts as a pump. When you feed this thing an ATP, in response to being given an ATP, it moves out of the cell 3 sodiums, and it moves into the cell at the same time 2 potassiums. And so that's what sets up this slightly negative. When I get out to the edge of my screen here, it gets a little wonky. So this is what makes the interior slightly negative compared to the exterior, is that every time you feed it an ATP, we get 3 positive charges added outside and only 2 positive charges added inside. So there we have our resting membrane potential, minus 70 millivolts. So this voltage differential then can set up some more exchange of materials across the neuron membrane. And so before we can talk about how ions are capable of moving across membranes, we need to talk about the kinds of channels that are found for ions to move. Now, ions are incapable of passing through the plasma membrane that surrounds a neuron. So here we can see the phospholipids. Here's the polar head. Here are the nonpolar tails, right? So they're all arranged like this. The nonpolar tails create an environment where ions are not allowed. It is not a place that ions can interact at all. And so in order to get ions to move from one side of the membrane to the other, then we have to place in the membrane itself a protein, and here we show our protein, that is shaped as a channel. Now, you might say to me, hey, that looks like a solid structure, not a protein. Well, you have to imagine that this is, like a chain of amino acids that is arranged in such a way that it creates this donut-like shape that allows ions to move from one side of the membrane to the other. So neurons, and other cells as well, but since this is really about neurons that we're talking, they have lots of passive channels, or sometimes they're called leakage channels. These are just channels that never close. They're always open. And so if there is a chemical gradient, then ions, like potassium, are capable then of diffusing from one side of the membrane to the other, following that chemical gradient, that concentration gradient, moving from areas of high concentration to areas of low concentration. And so potassium channels are an example of this kind of passive or leakage channel, because they've just got these holes in them that potassium can just go through. Now at rest, because the exterior, let's pretend that this is the exterior, has so many sodium ions, there's a lot of positive charge out here. So in general, potassium ions don't diffuse out through these leakage channels because there's so much positive outside that it kind of repels. So there's the likelihood of an ion moving out is always going to be this balance between the chemical gradient, the concentration gradient of the ions on one side versus the other. And then it's also going to have a component of what's the electrical gradient like. And so we talk about that combined gradient as an electrochemical gradient that determines how things move through these kinds of leakage channels. Okay, so leakage channels are one kind of channel protein. The other kind are active channels, or sometimes they're called gated channels. And these are channels that open or close in response to some sort of signal. And the neurons and muscle cells, because they have gated or active channels for sodium and potassium, that gives them their electrical excitability, their ability to respond to differences in electrical charges based on the opening and closing of these gated channels. So what are the signals that can be used to open or close a gated channel? Well, there can be chemically gated channels. These are channels that open and close when a neurotransmitter or some other signal chemical binds. So for instance, what we saw at the neuromuscular junctions of, where a neuron and a muscle are coming close to each other, is that binding of acetylcholine causes sodium channels to open up, so that sodium will follow its electrochemical gradient and will flood into the cell. So there can be chemically gated channels, and there can be voltage gated channels. So these are channels that open as the membrane potential changes. So the membrane potential may be minus 70, let's say, but if something happens, changing the membrane potential, making it more positive so that the inside reaches, say, a plus 55 millivolts, then that may be a signal that will open the channel, cause its gate to come open. Okay, so two kinds of gates that we see in these active channels. Now there's also a third possibility, or a third way that channels may be opened or closed, and that is that we can activate or inactivate these gated channels with time, with a time-gated or not a gate, but a timed activation or inactivation. So once the channel has been open for a specific amount of time, sometimes there can be a portion of the protein that will then block the entrance, so that even if the channel is open, it is now blocked by this what's called a time-sensitive gate. Oop. Stop it. Sorry about the scrolling here, and it's tough because if I get my hands anywhere near the screen, then it can sometimes change the slides. Okay, so chemically gated channels, voltage gated channels, and then the potential that there could be a time sensitive gate associated with a voltage gated channel, especially. Okay, so we've now seen how we can move ions from one side of a cell membrane to another, and that let's see, there we are. Okay, so that then sets us up for the opportunity to talk about how we can change, or the kinds of changes that we can see across a cell membrane. And there are two kinds of potential membrane potential changes. So we can change away from resting membrane potential in two ways. The first is called a graded potential, and so I've also talked about it as a local potential change. This is a potential change that does not travel very far from the origin of this potential change. It's a very short distance signal, and they're usually very small and they're brief. They don't last for very long. And where we see them occurring is either at the dendrites or on the surface of the cell body. So if an axon terminal comes up here close to this dendrite and releases a neurotransmitter, then that neurotransmitter will open up a chemically gated channel that will allow sodium ions to flood into the cell. Or perhaps it will allow potassium ions to leave the cell, causing either a depolarization or further polarization of the membrane. And so that graded potential can spread so that nearby voltage gated channels may open up in response to having a voltage gated, or the chemically gated channels open, causing a small potential change that will open other nearby voltage gated channels. And so we can see the short spread of a very small, brief potential change. Now, if this potential change is one that opens up sodium channels and allows sodium into the cell, then we think of this as excitatory transmission, because that further depolarizes, or it depolarizes the membrane. It helps to make the inside a little more positive. If, on the other hand, it opens up potassium channels, then we think of that as inhibitory transmission, because it takes, rather than moving the membrane potential in a positive direction, opening potassium channels and allowing more potassium to leave the interior of the cell would only make the interior even more negative, getting it further away from the chance that it might stimulate an action potential. Action potential, you ask? What the heck is that? Well, it is a large but also brief signal that self-propagates, that will spread all the way down an axon, can go very long distances, say all the way down the length of your leg, out down the axon, through the axon, the branches at the end of the axon terminal, reaching that axon terminal at the very end of the axon branches. So action potentials occur on the axon only, and they can be self-propagating. And it requires, before an action potential can be produced, it requires the axon hillock, this region right here, where the axon arises, the axon process arises from the cell body. It requires the axon hillock to reach a level of depolarization, of change in resting membrane potential in a positive direction of plus 15 millivolts. So we have to increase from minus 70 up to a minus 55. So that's a 15 millivolt difference in the positive direction. We have to get that axon hillock to get to that. Not sure what's up with my pen. Oh, it's because the cat is now lying on the keyboard, you beast. Okay, there we are, much better. Okay, so how do we get the axon hillock to experience that much of a change in membrane potential? Well, it's the job of those graded potentials. If we get, say one graded potential coming in and another one coming in, and each one of these little graded potentials coming in carries with it a plus 1 millivolt change in the positive direction in the resting membrane potential. And all of these arrive, if 15 of them arrive at the same time here at the axon hillock, then that will change the membrane potential of the axon hillock, and it will bring it to threshold, and then an action potential can arrive. If, on the other hand, we get a bunch of inhibitory graded potentials arriving at the axon hillock, then it's going to be no chance of the action potential being generated. So the job of the neuron is to do a little math right here at the axon hillock. Let's say it receives plus 20 millivolts. You're thinking, oh, hey, we've reached this minus 55 threshold. In fact, we've exceeded it. But if it also receives inhibitory stimulation to the amount of, let's say, 7 millivolts, then that means in that instant the axon hillock will have only received a total of plus 13 millivolts, not enough to reach threshold. So the job of the axon hillock is to add up the excitatory, subtract the negative or inhibitory transmission, and if it's enough to create a plus 15 change in membrane potential, then we can see an action potential being stimulated and sent along the axon. Phew, lots of stuff. So what does an axon or action potential, look like? Well, if we were measuring, and so here's where I've given you a lot of information. This is my summary of what the book had to say about what an action potential looks like. And so I want to encourage you to read it. And the thing to know about action potentials is that they are all or none responses. If the axon hillock comes to threshold, a plus 55 millivolt membrane potential, then there will be an action potential. But it will be an action potential like every other action potential in the entire world. So all action potentials are exactly the same. If that axon hillock only comes to a plus 14 difference in membrane potential, there will be no action potential at all. I think in class I said it's a little like being pregnant. Either you're pregnant or you're not. There is no, I'm sort of pregnant. It's an all or none event, and that's how it is with action potentials. If you get an action potential, then you're going to get the whole action potential. If you do not reach threshold, you'll get nothing. Okay, so what is happening when a piece of the membrane experiences an action potential? Something doesn't seem right. Yeah, I got too far. So the first step, here we are at rest resting potential. When the membrane receives some graded potentials that raise it up to approximately plus 15, so that's minus 55. That would be the difference between 70 and minus 55. Once we reach that point, then we see the sodium channels opening wide, and boom, in flood sodium channels, or sodium ions, and the interior becomes way more positive. In fact, it drives the voltage all the way up to plus 30 millivolts. So that's a big change. From minus 70 to plus 30, that's a 100 millivolt change. So that's 1/10, yeah, 1/10 of a volt change that occurs over the course of an action potential. So that's the first step. And we call it depolarization because, normally the interior of the cell is negative and the outside is positive. What we see during this moment is that this piece of membrane becomes very briefly, for only, a millisecond or so. So here we are moving up, and here we are coming all the way back down again. That's the course of 1 millisecond, 1/1000th of a second. We see that section of the membrane reverse polarity. It depolarizes so that the interior is more positive and the exterior is more negative. And depolarization occurs because the sodium channels open and sodium floods into the cell. Now the next step of an action potential is that same piece of membrane will repolarize. So here we are in half of a millisecond. It is going to drop back down again from a plus 30 up here at the top. That membrane voltage drops down to minus 70 again. And this happens because the sodium channels are becoming inactive, and the potassium channels are finally getting around. They are voltage gated as well, and they're finally getting around to responding to this voltage change coming to threshold here. So it takes them a while to respond, but when they respond, they finally open up, and now sodium has stopped coming into the cell, and now all the positive potassium ions are leaving the cell, and that causes this precipitous drop in membrane potential again, from plus 30 all the way back down to minus 70. And and we're going to see in a second that those channels, those potassium channels, stay open for a while longer. They're slow to open, they're also slow to close, and so because of that, we see hyperpolarization. So if this is minus 70 right about here, then the potassium channels stay open long enough for it to drop down to like minus 77, minus 78, somewhere in there, millivolts, of course. And then over time, the sodium-potassium pumps go to work. They pump, give them an ATP, and they pump out 3 sodiums. They pump in 2 potassiums, and in this way, we come back up to resting membrane potential again. So that is that section of the axon that has now gone through an entire action potential cycle. And so the thing to know, if we've got this section here that goes through an action potential cycle, and then it reestablishes the resting membrane potential, well, that brief change that happened here, this section, is going to stimulate this section to now do a depolarization. So the interior becomes positive and the exterior becomes negative. And then it will repolarize. But in the meantime, that depolarization here stimulates this portion to depolarize, and so on. So this is how we propagate an action potential along the length of the neuron's axon's membrane. can. No, that was pretty fast, but again, you've got the interactive physiology video that you can spend some time with too that will help you make some sense of this. Okay, the last thing then to talk about are the refractory periods. And we have two refractory periods that are associated with the action potential. A refractory period is a time when it is either difficult or impossible to start a new action potential. And so the absolute refractory period, oops, that's not what I meant that open, we are, is this timing here. So as the sodium channels begin to close, and that's all happening through this time here, as they begin to close, and we go through a period when the sodium channels remain closed because of the time-gated or the time-sensitive gate, there is no possibility of an action potential occurring. It doesn't matter how much stimulus you apply. You could hook your car battery up to this thing, and you could hit it with 12 volts, which is a huge amount of electricity compared to the electrical charges there at the cell membrane, and it still would not start a new action potential. And that's because those sodium channels are closed, and they are not going to open back up again until a very specific period of time has passed. So the value, or one of the reasons why this is important, knowing about this absolute refractory period, is that if this is an axon again, and here it is negative, positive on the outside, negative, positive, and negative, positive, and here is a section of membrane that is just going through the action potential. It's depolarized, and now it's repolarized. That depolarization that occurred cannot travel backward. It can only travel forward because this portion of the membrane is in the middle of the absolute refractory period. And so as the timed gates on sodium channels, those time-sensitive gates on the sodium channels begin to open again, that now allows the opportunity for an action potential to be generated in this section once more. But by that time, this action potential would have already spread down to this or this section of the membrane, and so there's no chance of it trying to stimulate something that's this far back upstream. Okay, so I said now that it's possible for an action potential to be generated during this period of the action potential cycle. And this we refer to then as the relative refractory period, or where there's a chance, but you have to give it a relatively hard hit in order to get that action potential to be stimulated. So the sodium channels are beginning to open up again. So it's possible to flood sodium into the interior of the neuron. But look at what resting membrane, or the membrane potential, is during this time. It's not just at a minus 70. It's now at like minus 77 or minus 78. So in order to get this membrane up to threshold, you don't just have to give it plus 15 depolarization, but you have to give it the additional 7 or 8. Well, let's just put in 8 millivolts here. So it requires a total of 23 millivolt depolarization in order to stimulate a new action potential here. So it's possible to do it. You just have to give it a lot more of a graded potential change, or changes arriving here at the axon hillock in order to get this section of the cell membrane to leave its relative refractory period and undergo another action potential, a new action potential. All right, so there you have it. At the end of the relative refractory period, then resting membrane potential is restored fully by sodium-potassium pumps again. Okay, so you know what to do. If you have any questions, give me a call, send me an email, and we'll talk to you soon.